Bismillahirrahmanirrahim. During last two classes, so we have discussed on the very basic on the conversion from the time domain to discrete domain, and we have also tried to learn about the frequency domain representation after doing the sampling, that means discretization of the signal. What would be the impact in the frequency domain? And there is a portion we have also covered, that is aliasing part and how to tackle the aliasing. Probably we know from our very basic understanding of DSP that we need to focus on the sampling frequency to cover the aliasing signal, aliasing part of our discrete signal. However, from any unknown signal or your input signal, this is xt in the time domain, first of all, we need to know about the maximum frequency content you want to process. So what would be that value? So conventionally, by doing research, people actually understand that value. For example, if the xt is a voice signal, we know that that is from mostly very close to 0 to 20 kilohertz. So this is the audible range, the voice signal. However, we also know that our signal basically implanted, most of the energy of our voice signal is implanted between 0 to 4 kilohertz. So it is obvious that we can cut down the higher frequency component. So first of all, if we try to put it in the block diagram, so if we have xt, first of all, we'll put it through a low pass filter, and the output of the low pass filter will give us, of course, an analog signal xt. I'm putting hat, where the maximum frequency, we know the maximum frequency now, and which is the cutoff frequency of the low pass filter, and let's say that is 4 kilohertz. After finding this, since we have we know the maximum frequency, then we can choose our sampling frequency at least 8 kilohertz, let's say more than that. So it would be greater than equals to twice of f max value, and this is analog to digital converter. And now we have our xn, and you can do the manipulation. What kind of manipulations? Any sort of filter. Though any sort of discrete system is a filter, number one. And number two is any sort of even analog system is also works like a filter. For example, a copper wire, when we are talking about a copper wire, you are giving some kind of input, and you want to get the signal from the other end. Whenever you are increasing the frequency here, whenever increasing the frequency in the input, of course, you'll find that after a certain frequency range, you are not getting the original signal, actual original signal. There would be some definite decay for the path, as well as there are some filtering. So if you go to the frequency domain behavior of this wire, then you'll find that it actually works like a low pass filter. So any sort of system like wind, even copper wire, or any sort of system in they are actually working like a filter. So in the discrete system, all the system works like a filter. So again, from the output of that one, so after having the output, let's say this is yn. From the yn, we need to again put it through digital to analog converter, and afterwards, let's say this is a This is a mic. You are putting the voice signal here, and at the end of the day, there is a, this is a microphone, and this is a mic, the sound system that will give us the sound. A very practical examples could be given. So we have actually talked about how this discrete signal behave in the frequency domain based on choosing the sampling frequency. So we have done this part in the last few classes, last two classes. Today, our main concern is to understand the discrete time Fourier transform. So we need to go through that. And from my experience, we need to understand from the continuous time Fourier transform, and that will help us to understand the discrete time Fourier transform very well. And during this course, we'd like to understand the process very deeply, not much about the mathematics, because whenever you need to implement it through mathematics, you can implement that if you can understand the algorithm properly, because the algorithm is very simple. But I don't know, sometimes people represent the things in a difficult way, probably, or we can understand those things in a difficult way. This is very simple. In a very let's say in a very simple manner, we can say that the continuous time Fourier transform is nothing but a combination of correlation. So this is correlation with what? We have a signal xt, and we have a known signal. So this is an unknown signal, and we have known signal e to the power minus j omega t. Here e to the power minus j omega t is a known signal, where this omega, what is the range of this omega, is from minus infinity to plus infinity. What does it mean? Think about original frequency. It is better to say from 0 to plus infinity. That is the range of this omega. Whenever I will put this omega, this is angular frequency. This omega is equals to twice pi capital F, where this capital F is the frequency in hertz, cycle per second, cycle per second. What is the range of capital F? That is from 0 to infinite. And since you know that in the frequency domain, that always useful to write it from minus infinity to plus infinity for the mathematical purposes. So here, this term mentioned that how we could write this term e to the power minus j omega t. So by definition, if we have xt as an input in the time domain, in the frequency domain, we can represent it like x omega in the frequency domain is equals to making our xt multiplied with e to the power minus j omega t, making the integration from minus infinity to plus infinity, and that should be differentiated with respect to time. And this is all about the Fourier transform. In this term, we have two things. One is magnitude, of course, and another one is the phase of x omega. There are two parts. We can find it from this single equation, both the magnitude and the phase. As you can understand that, if we can elaborate this equation, we can find it x. We use the capital omega for analog system. X omega is from minus infinity plus infinity xt e to the power minus j omega t and dt. it can be elaborately written as this part, since this is the Euler's from the Euler's identity or Euler's formula, we can write e to the power j omega t is equals to cos omega t minus j sine omega t. Here the amplitude is 1. If it is a, then it will be a cos omega t minus j a sine omega t. Okay, so you can write it here. This is 1 and this is here is on 1. So we do not need to write it there. We need to understand it by graphical representation. So first of all, by mathematical terms, we can elaborate those things, and then after graphical representation, we want to understand this part. Okay, so if I put this term over there, replacing e to the power the exponential term, we can write it in this way: xt, then cos omega t, and put integration from minus infinity to plus infinity. That is this term minus infinity to plus infinity, that is a function of omega. So we are talking about the omega minus j. We can put j in the before the integration, because the integration is not a function of omega. So minus infinity to plus infinity, then xt sine omega t, and of course there is dt. Okay, I forgot this dt. So you got, so now we have two parts in our equation. Let's say this is a and this is b. So we can write x omega is equals to a minus jb, where a is equals to integration minus infinity plus infinity xt cos omega t dt, and b is equals to integration minus infinity plus infinity xt sine omega t dt. Here we need to concentrate on both a and b part. What does it mean? By this equation, we can understand we have our xt, full signal unknown, and we have known cos signal. Why that is known? Because we will try it for all the possible value of the omega. That's why it might be useful to write in this way: the a part and b part. A is also a function of omega, and b also a function of omega. Whenever we need the omega equals to 0, that shows the DC value. Omega equals to 1, 2, 3, whatever the value. But the omega, again, the omega is equals to what? Twice pi capital F. So you can choose the value of f, capital F, and for different value of capital F, like starting from the 0, 0.1, 0.2, it is a continuous one. For different value, you have this part, and what you are doing, we are doing the correlation between our unknown signal, to our known signal. If you do the correlation and make the summation, after making the multiplication, if you go for the summation, if they have good correlated value, then you are getting higher value. And if you have less correlated value, you will go for less amplitude whenever you are summing up. So now what I'm doing, let's say this is equation number 1 and this is equation number 2. For a particular xt, I would like to show you how we can find a omega and the b omega in the next section. Let xt, how it looks like. Let's say the xt looks like this. For simplicity, I'm taking a pure cos signal. Okay, it can be, what is the range of it? It is, let's see that, let's take that it actually came from minus infinity and it's prolonged to the infinity, positive infinity. So what is this? This is your xt unknown signal. We do not know the frequency of that signal. Now, what is the second one? Let's say we are targeting a omega. What is a omega? So first term is xt. Second term is cos omega t. What would be the frequency you should target? Any value. First starting from the DC, then any frequency value you can imagine. Fortunately, let's say, and what is the amplitude here? Amplitude of the cos signal, the amplitude of cos signal is always 1. And what about xt? Let's say the higher value of the xt here is, let's say, 0.5. So if I got the cos omega t, I want to draw it. This is by any means, don't take it otherwise. You are getting this cos signal by any means. Since you are sweeping the omega value, you are starting from 0 and you will move to the infinity. Definitely in one time it will match with your unknown frequency, and we are at that position. So this is step number 2. So we need to put our xt, and then we are putting what? Our cos omega t, where omega actually fit with our unknown signal. What would be the next step? The next step is we need to multiply these two factors. We need to multiply, not convolution, so don't confuse with that. So multiply these two factors in the time domain. So if I want to multiply these two, of course, each and every point should have a multiplying value. So let's say this is 1 multiplied with 0.5. So it will give you 0.5. Then this point should have a multiplying factor. The amplitude should be positive or negative. Of course, that should be positive. And up to this point, all the values should be positive. And whatever the value, I'm just arbitrarily I'm writing here like this. Okay, not. Yeah, of course it will goes to the 0. And for this section, that means from this to this, all the values you can find, we have negative multiplied with a negative value, so it will give a positive one. So again, we are getting some positive value like this. And from this to this section, we again got a positive value. We are multiplying the things. And since they are continuous, xt and cos omega t both are continuous, of course we'll get the continuous values. Of course we are getting continuous red lines over there. What we are doing, we are multiplying each and every point of the xt and cos omega t for a particular value of the omega. Okay, nice. Now after that, what we need to do, we need to go for integration from a minus infinity to plus infinity of dt, minus infinity plus infinity with respect to dt. Here omega is a particular value, but time frame is from minus infinity. So as I already mentioned that it actually came from minus infinity and it belongs to plus infinity. So whenever you sum it up, definitely, so you need to be very precise in this point. If you sum it up, definitely the summation gives infinite value here, because you have positive values. So if you sum it up, definitely it gives a huge number. So in practice, what actually it given, it gives an average value. After doing this, to represent it in the physical phenomena, we need to make an average of what should be the dividing factor, the total time period. In practice, we never do the continuous Fourier transform. We always do the discrete time Fourier transform. However, for this case, let's say the time frame is t. Let's say the time frame is t. My concern of the point is that after doing this processing, that means by doing multiplications and doing the integration from minus infinity to plus infinity, whether you are getting some positive number or negative number. Of course, you are getting a positive number. And let's say we are getting that positive number for this omega, where this omega is equals to omega 1. So that means for a omega 1, you are getting some value which is greater than 0, and which is a very high value, because you have a very high correlation between xt and the cos omega t. We have a very high correlation because they are looks like the same, not again in the amplitude, but in the frequency. Okay. Now, if I move to another frequency higher than this, for example, this omega 1 was, let's say, okay, first of all, let's think that this is the cos part. That means we are targeting the A portion, and we have done that. Now we'll move to the B portion, how to calculate the B part. Okay, let me erase the things. I want to preserve the black line only. Okay. And now what we can do for the B part, B omega, we have already know that it is equals to xt. First of all, yes, we have that signal. This is our xt, and then multiplied with sine omega t. Let's make it omega 1. This is omega 1. So where is sine omega t? With the same frequency of our xt. We do not know about the xt, but fortunately, let's say omega 1 and the frequency of xt are the same. So now if we draw the the sine omega t, how it looks like should be like this. Okay, let me try to draw it precisely with the amplitude 1. Amplitude 1. So it will be higher than this. Okay, just think about in this way. Okay. So this is now sine omega t, omega 1 t. And now if we target, what would be the next step? Next step is a multiplication. So again, we can multiply in different portion so that we can understand the process. If you can think of it, for the portion, this portion, both values are positive. So that's why you are getting some output like a positive value. For this portion, that means for this portion, you have positive value for the sine theta, sine omega t, and negative value for xt. So that's why the multiplication gives a negative number. I should choose another color. So this is a positive, and here it will give a negative. For this section, the third section, again, both of them are negative, that's why we are getting a positive number. For other section, one is positive, one is negative, so that's why we are getting a negative value. And if we move on, we'll get the same thing again and again. And of course, they are continuous. So you got an area under the curve. So area, you are getting some kind of area if you go for integration, because for each and every point, you are getting some number. And it will continue. Now, if you go for the integration from minus infinity to plus infinity to plus infinity with respect to time, of course, you can find that there's some positive and some negative, positive and negative, positive, and there will be some negative, and they will cancel each other. And ultimately, you can find that the b omega 1 is approximately 0, exactly equals to 0 in hypothetical term, but in practical term, we can say that it is very close to 0. So if you can recall the whole process, in case of this kind of signal, it's very important to understand what kind of signal is this one. This is xt, that is unknown. What we have found here, we have found two things. Our x omega is equals to, let's say, a minus jb. What is a? It is integration of xt and cos omega t dt minus infinity to plus infinity, and minus j and then b part for the sign. What is the value you have found here for a part? We have already mentioned that there is a significant value, is more than 0. Let's say the value is 1. Not like 1, okay, let's have any value, let's say 0.5 or 0.8, whatever the value. You are getting some value more than 0. And what about the b part? You are getting j, b part is very close to 0 or approximately 0. You can say that is 0. So that means you have only the real portion. For more simplicity, let's say this is equals to 1. So you have 1 and minus j 0. For which frequency? This is for omega 1. So now in the frequency domain, if we want to plot the magnitude response x omega, what is the formula? A square plus b square and root over. And where a is 1, square plus 0 square root. So that will give exactly 1. For which frequency? For omega 1. So now you can plot the magnitude response where this is omega and this is what? This is x omega magnitude. Where is that omega 1? Let's say this is omega 1. At the location of omega 1, you got a stem 1. Of course, for a minus omega 1, you will got the same value. This is another matter, but this is the fact. What about the phase? This is a magnitude response of what? The magnitude response of xt. We have drawn that. If we want to draw the phase response, what would be the phase value? Very simple. Again, this is omega and this part is the phase. For which frequency? For omega 1. What would be the value of the phase? The phase is equals to, of course, this phase is also a function of omega. So this is for omega. This is tan inverse b by a, where b is 0. So we can write that this tan inverse 0 is 0. So that means the phase is equals to 0. Phase 0 means what? From the phase 0, we can understand this. this signal, unknown signal, is a pattern. What is the phase? From this phase, we can understand the phase of this signal. When the phase shows 0, it shows that this is a purely cause signal without any delay or any progress. And from the magnitude response, we can understand what is the frequency component you have inside the unknown signal. And what is the frequency component? This is omega 1. Now, if you can extend this example like this, let's say that this is your known signal xt for a frequency. This is xt for a frequency. Let's say in some way we can find that this is f1. You can find that if you put, or if you try for any other frequency rather f1, whether this is a cos omega t or sine omega t, what we have shown, for any value rather than f1, for all the cases, the a omega should be equals to 0 and b omega should be 0, and this is true for all the value of omega, and this is not true only for f1. And because only for f1, why I'm talking about f1, this is omega 1 is equal to twice pi f1. Only for f1 you have some positive value or some negative value when you are summarize the things, minus infinity plus infinity, and that can be proven by the graphical representation. However, if you go for any other frequency, let's say omega 2 is equals to twice pi f2, whatever the frequency f2 is there, it will not match, and in that case you will find some positive value and some negative value, and whenever you are making the integration or the summation, in that case that will nullify and it will actually give 0 value in the output. So for this kind of single frequency component, of course you get a single frequency output in the frequency domain, as we have shown, like, sir, this is for omega 1 and this is for minus omega 1. But if that is a multiple frequency, definitely you will get multiple stem in the output. Okay, so I used to give this lecture when I have talked about the continuous time Fourier transform. This is, to my understanding, this is a very good example to understand the process. Let's say here, probably it is not very visible to you, so that's why I'm just writing it. It is written that the ft is a signal which contains 0.6 sine, let's say, omega t, and plus the second signal is 0.8 cos omega t, where this part, this frequency, the frequency of sine omega t part contains 3 Hz, and the cos omega t contain 8 Hz. That actually represent by this signal. So this is our xt, unknown signal. In some way we know that, okay, this is 3 Hz and this is 8 Hz, but eventually this is not known to us. Okay, let that we do not know those facts. Okay, now we can go step by step with the process we have already mentioned. So as you can see in that, the black line is there. Black line shows our xt, unknown signal, and this green line shows the sinusoid, the cos signal with 3 Hz. Just arbitrarily we have chosen 3 Hz. We should start with 0 point something, 0.5, 0.8, 1, 2, 3, whatever value you want. Okay, but arbitrarily we have chosen this 3 Hz. And we have also chosen 3 Hz for the sine part. So from there, we'll got the essence of A3, and from there, we'll got B3, where 3 mention the frequency. Okay. So if we move on, this is the second step where we are multiplying each point. So if we multiply the things, I can go faster. Whenever we'll multiply the unknown signal xt with our known signal cos twice pi 3t, so then we got this kind of area. So you have seen that there are some positive, negative, and from your naked eye, if you sum up all those things from minus infinity to plus infinity, you'll get approximately 0, because numerator and the denominators, they will cancel each other. And if you sum up here, what you are getting, you'll find that in the denominators or the lower portion, you are getting less value than the upper portion, and that is expected. That is expected because, as we can know, that our input signal or unknown signal has 3 Hertz component, and we got that whenever you are getting the summation or taking the summation from minus infinity to plus infinity, you'll find a value more than 0. So what does it mean? It means that at 3 Hertz, or you can say twice pi into 3, so at 6 pi, so at the omega level, in the frequency, we can say that at that moment we have the frequency. Let's say we are writing the magnitude response. Of course, in the magnitude response, we should have a stem at the location of 3 Hertz or 6 pi. Okay, so let's say this is the stem, and this is for 6 pi, and this scale is for the omega value. Okay, we have found that because there is a b. If we have the b and a is 0, eventually a squared plus b squared root over, so you are getting some value over there. Okay, if we move on and if we increase the frequency and choose the frequency as 5 Hertz, in that case, if we proceed on, we'll find that this summation gives almost 0. From your eyes, just a average calculation, you can find that is very close to 0, and it is also true for this, and which is expected because in our unknown signal ft, we don't have any 5 Hertz component, so there shouldn't be any match from a part or from the b part, a portion or from the b portion. Okay, so if we move on and try for 8 Hertz, what will happen? We are expecting this 8 Hertz, and if we try for the cos, it looks, yes, you can find that more positive values are in the top side than the lower side, and it is a very good match, and we got a higher value for a, and I should write a8. That gives very higher value comparing to the 0, and that is expected because, as you know, that in our unknown signal there is a cos part and which contains 8 Hertz signal. And if we think about the b portion, since that is the b portion, the sine part 8 Hertz, there is no component in our signal. Of course, we don't find any value over there, so the summation gives almost 0. So since there is a match again, we got a match again, then we got another stem at the location of 8 Hertz because we try it for the 8 Hertz, and 8 Hertz means again twice pi into 8, so that is 16 pi at the location of 16 pi. That's it. This is in the frame of continuous time continuous time signal. Of course, we got to a stem in the negative side, so no need to mention it. So this is all about what the f omega. F omega means this is the magnitude response. If we talk about the phase response, definitely we need to consider A and B both, and the both cases in two cases, like for two stems, there would be two different phases, because as you can find that whenever we'll target the 6 hertz or 6 pi, 3 hertz or 6 pi, in that case, since this is a sine signal in reality, so the phase will be given as what? What would be the phase value? What would be the phase value you are expecting? Can you guess? If your unknown signal is a sinusoidal sine signal, then what would be the phase? It gives 90 degree, definitely, because the cos shifted for 90 degree is actually the sine signal. As we have already shown that if your unknown signal is a cos signal, starting with 0 phase, it actually shows the reference, it shows the 0 phase in the phase diagram. So whenever we have shown something in the phase diagram, let's say this is the phase diagram, this is phase, and this is with respect to omega. Let's say in some point we are putting 0 phase, and let's say phase is pi by 2. This is phase pi by 2, 90. So let's say we have two stem. If I draw the magnitude response side by side, okay, this is the magnitude response. This is f omega magnitude response, and we have shown that, okay, we have two stem. This is omega, this is omega. For this stem, we got the phase, let's say, okay, it should be vice versa for our case. Let me show it here accordingly. Let's say this is this, and this is 0. Let's say this is for 3 hertz, and this is for 8 hertz. What does it mean by this magnitude response and the phase response? We can discuss it. Okay, we have 3 hertz and 8 hertz component in our unknown signal ft, where 3 hertz component has the phase 90. That means this is a sine signal, and 8 hertz component that has 0 phase, that means that is a cos signal. And then we can write properly that, okay, ft is equals to sine omega t plus cos omega t. I can write here 3 and here 8, just to mention that this is 8 hertz and 3 hertz. We are missing another part, which is that what is the amplitude of that? Definitely this amplitude shows the amplitude of this stem. If the amplitude is higher and lower, based on that, you can put this amplitude. We can find this amplitude. So what I try to make you understand that by having this phase value and the magnitude response, we can understand our unknown signal properly. Where the two parts are, one is frequency component, as well as we can find the magnitude value of that signal, as well as we can find the phase part of the signal. Okay, at this moment, if you have any comments. Okay, fine. So extending this example, okay, if you try it for 30 hertz, of course, the summation should give 0, and this summation could also give 0. So there is no component like this. And if we try it for this kind of signal, where this signal is a combination of lot of sinusoidal signal, that is not a pure sine signal. So of course you will get a lot of signal over there. And how you can try it? Let's say this square wave, which one is given here, square wave. The square wave actually has the 3 hertz frequency, because within 0 to 1 second we have 3 pulses. So 1 pulse, 2 pulse, and 3 pulse. So first of all, if we try the 3 hertz signal of causal signal, cause signal, what we have found, we have a lot of negative. So that means we have A, let's say for 3 hertz, I put 3, that is equals to that they have found this value minus 0.5551. So you got the value. So whenever you do the square of that, of course you got the value. So whatever the value, whether this is positive or negative, both makes the same sense. Okay, it actually matters when we are talking about the phase. What about B3? We are getting some value over there. We got the value 0.31614. So it means that this square wave must have 3 hertz component, and the value is very high. The content of the 3 hertz is very high, because you got this value. So that means what is the magnitude response? 0.5551 minus whole square plus 0.316 whole square, and then root. You are getting very higher value. If you proceed with some other frequency components, let's say for A4, A5, A6, you will get some small numbers, but still you got the number. For example, here it is for, let's say, tried for 6 hertz. It is not exactly 0, you are getting some number, because our square wave is not a pure sinusoidal signal. That's why definitely other components are you can find other components. So if you plot it in the magnitude response curve, then we found that, okay, at the 3 hertz, you are getting the peak. You are getting at 3 hertz. However, you can also find some other component very close to that. So that means there you can find some spectrum value for this square wave. If the square wave is large, that means if we have higher value, more like high lower frequency, let's say like this, what we are expecting, low frequency component. So this line, in that case, this line will shift little bit to the left. Okay, what you are expecting in the previous case, that means the square wave as it is in our case, when the square wave frequency is 3 hertz, in that case I have shown that, okay, this is the peak, and you will get some spectrum like this. Let's say I give the name of this spectrum is P. Can you expect when the frequency is 2 hertz, this square wave having 2 hertz, so this point is for 2 hertz, what would be the spectrum? It will be, the spectrum will be higher or lower. I am writing 2 possible things, like the spectrum will be higher or the spectrum will be lower. Let's say I took another color. What you are expecting?
Higher spectrum, sir.
Sorry?
Higher spectrum, sir.
So you actually go for the black one.
Yes, sir.
Okay, the black one. Any other guess? Because there are two answers. Okay. Now, if I ask you why?
Sir,
Yes.
so because the signal strength, I mean, wavelength is very high. That's why we are getting more spectrum there. Spectrum value is higher than the, if we take more hertz, then the spectrum value will be low.
Spectrum value will be low. Okay, let me give you this example, then probably we can understand more. If your signal, that means your square wave, looks like very small indeed. And we are comparing with this. Try to understand number 1, number 2, and number 3. Let's say I just put a, okay. Number 3 is like a DC. So what we are expecting in case of number 3, if that is a DC value, in the frequency domain, in the time domain, if that is a DC value, what you are expecting in the frequency domain? In the frequency domain, we are expecting only the DC value, isn't it? Do you have any sine component or the cos component in the DC value? The answer is no. You got only the DC value. Are you agree with me?
Yes, sir.
Okay, fine. Now, whenever you are getting something like this, you can expect that, okay, of course, we have some frequency component, and let's say this is the frequency component, and we are getting something like this, something like that. So as you can understand, from this to this, from part 2 to 3, what we have done, we are expanding this portion. Basically, we are expanding this portion. We are expanding this portion more and more, and then come to the DC. And in case of DC, we are getting extremely narrow band. That means there is no other component. But if you move to the number 1, whenever you are putting this band in the time domain lower, then of course you are expanding the band higher. You are expanding the band higher. So that means if this is our example FT, we have started with that. If you decrease the frequency, the band will be also decrease in the frequency domain. Band means the extra frequency that will decrease if you downsample that. It is actually not downsample, this is upsample. But since we are in the time domain, if you increase the frequency, decrease the frequency, it actually decrease the spectrum as well. On the other hand, if you increase the frequency, or you can change this magnitude. For example, like this, if you have the magnitude like this, comparing with that, if you have this kind of course, which one has a higher bandwidth in the, which one need higher bandwidth in the frequency domain? Which one, A or B? Which one need higher bandwidth?
A.
Of course, B need higher bandwidth. B need higher bandwidth. What does it mean? Okay, let me give you this example. This is very important in the discrete Fourier transform. Let's say we have delta function. We can draw it, delta function. It's very simple. Okay, this is our delta function. We are now in the discrete domain. Okay, if we are in the discrete domain, now we are just jumping from the time domain to the discrete domain. Previously, our signal was xt. Now we talk about xn. What is xn? We know very well. So for n equals to 0, we have this stem. If we do the Fourier transform of this stem, then we can find what are the frequency component you need to build this stem. So what we need to do for discrete time Fourier transform, what is the definition? That is xn e to the power minus j, now omega, relative frequency, and n. Make a summation from minus infinity to plus infinity, and no d omega or dn, because this is summation. What is this? This is x omega. Previously, whenever we are write x omega for continuous time Fourier transform, it was integration minus infinity plus infinity xt e to the power minus j omega t. So you can compare with these two equations very easily. We actually done the same thing. Since this is discretized, now this is also discretized, and if you go along this, if you try to find a omega, it is also discretized. B omega, that is also discretized, but after making the summation, you are getting a number. What is the number? Let's say this is 0.5. Let's say this is 0.3, something like this. You are getting the number at the end of the day. But the process is a bit different because our xn is discretized and ej omega is discretized. Everything remain the same. Now, if you allow me, then if I draw this diagram, let me draw this diagram for you, how it should be, looks like. I'm talking about this one. If I want to draw it in the time domain, so how it looks like. Of course, it is in the time domain. I start with the same example we have given in the previous part. Let's say try to understand each and every portion, and if you have any question, please raise your hand and ask me. So what is this? This is our xn. Previously it was xt. We just sample it, and now we have those samples. And where is e to the power j omega n? Now it is, again, you understand that this is cos omega n and minus j sine omega n. So forget about this. So first cos omega n. What is cos omega n? What is the sampling frequency? They must have the same number of samples like this. So if I want to draw the cos omega n, they will have like this. Hopefully you understand the portion. So previously it was continuous cause signal. Continuous, this is a cause signal. And from that, we have drawn a discrete cause signal because now we are in the discrete domain. That's the difference. Now the second portion is we need to multiply each point. So multiply this, multiply this, and all over the places. You got some output like a stem. Now you are getting some stem. After multiplications, you are getting some stem like this. Stem like this. And now what you will do? You will do the summation from minus infinity to plus infinity. So sum up this one, this one, this one, this one, this one, this one. You have some positive number. Okay. I made one mistake that whenever you are multiplying this negative to negative, that will also give positive value. You are getting, for this example, you are getting this kind of thing. Okay. And now you are summing up. And whenever you are summing up, you found, okay, the A, that value of omega 1, this is more than 0. For B, omega 1, you are getting exactly equals to 0. From there, you can understand that, okay, this is a cause signal, whatever I have shown you in the previous segment. Now, come to the delta function. So if we took the delta function as our example, which is what? Which is our input, which is the input. So we can write it here, summation minus infinity to plus infinity. This limit is for n, minus infinity to plus infinity. Xn is what? Our delta function, e to the power minus j omega n. So we need to do the multiplication. This multiplication only can be done when n is equals to 0. Otherwise, all the value for n delta function is 0. That's why there is no multiplications you need. So only for n equals to 0, we can write this is delta 0. You do not need any summation because there is only one value. And e to the power minus j omega, and n equals to what? N equals to 0. So what would be the value? E to the power 0 is 1 and delta 0 is 1. So the output is 1. So this is our x omega. So we found x omega is equals to 1. What does it mean? It means that you can draw the magnitude response. We can draw the magnitude response. This is for omega, relative frequency. This is x omega, not capital omega, small omega. How it looks like? For any value of omega, the amplitude is 1. So for any value of omega, this amplitude is 1. Any value omega, amplitude 1. So it will continue. Again, for any value in the negative side, it will continue. How long we can continue this? What would be the limit? Of course, the limit is up to pi. And in the negative side, that is minus pi, because that is our range of view. To restrict the aliasing, we need to restrict our value of omega up to pi. After pi, you can go after pi, but there is aliasing. So we need to concentrate on up to pi. Whenever we ask you to draw the magnitude response, it is enough to draw it from 0 to pi, most of the cases. But in some cases, we need to draw it from 0 to twice pi or thrice pi, just to understand the process. Okay. You can understand it that for any value of omega, the magnitude is 1. What does it mean? from the frequency domain to time domain. Can you relate that? Any of you? Because my students should answer that. My previous students should answer this. What does it mean? X omega
Sir,
is equal. Yeah.
Sir, it means it has all the frequency components.
Can you make it more clear?
Yes, sir. The delta function, it has delta function. When we make it into frequency domain, it has all the frequency components.
Okay, that is one way. What would be the other way? That means if I go from frequency domain to the time domain, how you can relate that? Let's say inverse Fourier transform. If you do inverse Fourier, how do you relate this? It shows that you need all the frequency component. You need all the frequency component to build your delta function. Whatever you have given the answer, exactly correct. You are giving the answer from the time domain to frequency domain. That means whatever we can see here, delta function preserve all the frequency component. Or somebody can say that, okay, you need all the frequency component to build the delta function. Who is actually real? Time domain signal or frequency domain behavior? Which is actually real? In our life, both actually make sense, both frequency and the time. Whenever we are talking about the voice signal, we are listening in a time domain, though we are observing or we are having our response in our ear in a frequency domain. Otherwise, you can't differentiate between two voices with the same information. Let's say I am giving the information, person 1 giving the information, person 2 is giving the same information to you. Like a song, he's sing a song and he's also sing the same song. So can you identify the difference? Yes, we can, because we can observe it in the frequency domain as well. So mostly our ear or our sensing system, all the sensing system actually works in the frequency domain. There is another part, I need to finish it here. X omega is equals to 1 plus j into 0, because there is no imaginary part. It shows that what is the phase of x omega? The phase is tan inverse 0 by 1, which is 0. And if you can plot it, the phase, you can find what is the phase plot. The phase plot is 0 for any value from minus pi to plus pi. And as I already mentioned that you need two information. One is magnitude response, another is phase response. From these two information, what we can observe, this is very interesting. What are the frequency component you need to build the delta function? As already one of our friend already mentioned that you need all the frequency component. So how we can observe this? This is the way how we can observe. Do you need 1 Hz signal? The answer is yes. What should be the phase of that 1 Hz signal? Quickly, what should be the phase of that 1 Hz signal? 0, isn't it? Because all the frequency should have 0. So that means that is a cause signal. So I'm writing that. So this is 1 Hz signal. Okay, 1 Hz. Now, do we need 2 Hz signal? Yes or no?
Yes, sir.
Yes, you need 2 Hz. So, and what is the phase of that? 0. So that should be again like a cause signal. So I'm writing that. Okay. Do you need 3 Hz signal? Yes, the answer is again. And what should be the phase? That should be the 0 again. So it should always start like a cause signal. And if you draw like this and doing like this for infinity time, then what will happen? You can find that only for this portion, you are adding the things. Everything will add it up there. And for any other portion, they will subtract each other whenever you are adding all those signal together. Whenever you are summing up all the signal together, then you found that everyone is vanished. Only who will stable, only this signal will stable. And as I already mentioned, that you need to go for the averaging of that signal. Whenever you are doing the averaging of that signal, you'll find only this stem signal over there. And that is the like explanation of the delta signal. Why this delta signal is very important? Because as you know that impulse response actually tells many things. So in the next class, inshallah, I will talk about the impulse response and why this impulse response is important, and how we can find the convolution sum by this delta function or the impulse response. Okay. Okay, I believe that we don't have much time, because probably some of you have the other class with our Dean sir, Ashraf sir. Probably. Okay, let me stop here. If you have any question or comments, so please don't forget to ask me in the next class. Thank you for your participation. Thank you.